This series of videos is going to go over the equation y equals mx plus b, which is the equation of a straight line, and we're going to plot some data and fit that data to y equals mx plus b and see how well your data fit a straight line. So what we're talking about is plotting data in a picture, and I can't understand anything unless I make a picture of it. So when we are talking about the x value, we're talking about the horizontal axis, and it's on this axis where you're going to plot what you know, or your best estimate of the truth. So in the case of temperature, that is 0 Celsius is freezing, 100 Celsius is boiling. That's independent. That's the thing that is known. And for temperature, it's really great because there really is, at least on the surface of the earth, it's pretty much 0 degrees for freezing and 100 degrees for boiling all the time. So that is truly independent. And that's what you plot on the horizontal axis, and that's what we call x. So when you start putting your data into this chart, it's easiest just to have your first column be the x-axis, and that is the independent variable, and that's going to go on the horizontal axis. For example, ozone, you would be talking about the known ozone concentration that you generate with your ozone generator, and you may have something around 90 parts per billion, you may have something around 50 parts per billion, and you may even have higher parts per billion that you generate with your ozone generator that you know, or at least it's your best estimate of the real ozone concentration. And then vertical axis, this is where you plot your y values, and this would be the next column in your data table, and this is the dependent variable. In the case of temperature, you have a thermometer, and it may or may not be NIST traceable, and you measure the freezing point of your water in an ice water bath, and that should be 0. It may or may not be 0, but that's what you plot here on the y-axis. And that is called the dependent variable because, for example, where you're measuring something and you have your best estimate of the truth be on the x-axis, the known, then on the y-axis would be your measurement of that, and that's dependent upon whatever the truth is. So these are the two axes, the x-axis and the y-vertical axis. Let's plot our data. So let's assume that we are doing, let's just say ozone concentrations. We've got a 0 value where we're putting a gas that has 0 or as close to 0 as possible concentration of whatever it is we're measuring. And this could be temperature. Temperature works with these same units also. So let's say you're doing a temperature probe and you have an ice water bath and you measure, fortunately for you, you measure 0, and that is the first row in our table where we've got the first column be the x value or the independent variable. The y column, which is going to go on the vertical axis, is the dependent variable. That's what my temperature probe reads. And let's say a miracle happens, and for every known concentration, I get exactly the right answer with my temperature probe. So you can see how this is starting to form a straight line. So here we've got at the 0 axis, we've got 0 on the x right here, this 0, and 0 on the y right here. And these data labels are the x comma y value. So then for the next row where we've got 50-50, you go over here to this x-axis and you draw a line up till you get to 50 on the y-axis. And you can see that that's x comma y 50, which is down here on the x or the purple axis, comma 50, which is the y. Then let's say further miracles happen and you measure exactly 90 degrees. And then the last value is 100, and that's boiling for water. And you can see that that value up here is x comma y. Where these points are plotted on the graph is a little easier to see if you have grid lines. Now we are using a different thermometer. This is a temperature probe that was old and we found in the shed. So we measure what the shed temperature probe says in an ice water bath. And so it actually measures 10 degrees. And then what the temperature probe that was in the shed measures with a water bath that's exactly between freezing and boiling. And it measures 10 degrees higher again. And we measure it almost boiling, and And what the shed temperature probe says is 100 instead of the almost boiling. And then when we take the water bath up to boiling, it measures 10 high again at 110 degrees. At 0 on the x-axis, the shed temperature probe measures 10, and it measures 10 all the way up. So let's look at the trend line for this. So to add a trend line, you right click the series. You can see that there's those little dots that go around all the points, and then also you can see here in this drop down box you can select series 2, which is the second series that you added. And now what we want to do is right click and say add trend line. So I say add trend line, and then pops up this dialog box on the right, and what I want it to do is display the equation on the chart and display the r² value on the chart. And then I click X to close that dialog box, and you can see that it made a nice little box for me here, but I'm going to format it so we can look at it more easily. And it gives me a beautiful equation, y equals x plus 10. Well, all that means is for every row in my data table, when I've got the x of 0, I have a y of 0 plus 10. So I have a y of 10, which is where this first point is on the vertical axis. And then for my next point, I've got an x of 50, so that's here, right between 40 and 60. And I take that up, and it's 50 plus 10, because the y is going to be the x value of 50 plus 10, so it's 60. And so this next point is 60. It could be 60 degrees or 60 parts per billion if what was being plotted on the x-axis is ozone concentration, for example. And then the same thing for the next point. I've got an x of 90 and a y of 90 plus 10, which is 100. And then I've got a 100 on the x, and 100 plus 10 is 110 on the y. And what that means is, remember, the equation of a straight line is y equals mx plus b. So we've got an m here of 1, so that's why it's not shown in the equation, because it's the same thing. So you just let the 1 drop out because it's y equals x plus 10. So in this case, we have a y-intercept. If you take this line down and you trace it down to where it hits the y-axis, it hits the y-axis at 10. So here we have a y-intercept of 10 and a slope of 1. And you can see that our original line, which is our first series here, with our perfect thermometer, we have a y equals mx plus b, where it's also a slope of 1. And you can see that because these lines are parallel, so they both go a rise over run. So a 1-to-1 relationship. Every time the temperature runs across the x-axis by 1, your thermometer, whether it's 10 high or right on, it rises with a 1 also. So when you've got a slope of 1, like you have for both of these lines, you've got a perfect rise over run of 1-to-1. Every 1 run over on the x-axis corresponds to a rise up on the y-axis of 1 also. And both of these are perfectly straight lines, and you can see that because of the r² value of 1 for both of these. Let's look at one more case. Now we have a thermometer that somebody from the county has provided, and they're not sure how well it works or not. So we're going to assess it in the same ice water bath where we compare it with our perfect thermometer. Right off the bat, we see a low intercept of -10. So in the freezing ice water bath, our first point is 0 on the x-axis, -10 on the y-axis. So we don't think this is looking really good. If this is a temperature probe in which we could adjust the bias and we could bias it high, this might work, but only if we see a really good 1-to-1 relationship between what the thermometer measures and what we know the known is, in which case we could adjust it high by adjusting it based on the intercept. But let's look and see how good of a 1-to-1 relationship, or how close to 1 is the slope of our line. So the next halfway between freezing and boiling, it actually measures 75 degrees. So that's really weird. And that point we see right here where we've got 50 on the x-axis, and then on the y-axis we've got 75 degrees. And then our next point at 90, so almost boiling, it measures as if it's more than boiling at 105 degrees. And you can see that point is way high up here too. And then finally at boiling, this thermometer measures 145 degrees. I can see right away these are not in a straight line. but let's see that in graph form and look at the equation. So I select the series, and again, if I'm not sure, once I select something in the chart, that opens up Chart Tools. I go to Format, and I can see I've got Series 3 selected, which is what I want. If it wasn't right, I could click it here in this drop-down box. With that selected, I right-click, and I say Add Trend Line. And that gives me a trend line. I'm going to format it so that I can see it a little bit more easily. And with the Format Trend Line dialog box still open, I look at the data section here. You can see you could navigate between these various sections, but with the data section here on this line selected, I click Display Equation on Chart and Display R-squared value on chart. And again, that opens up this little box. I'm going to reformat it. And here's our equation. So you can see we have an R-squared of 0.9631. Well, I'm going to click in there and modify that so that my brain can get around it. An R-squared of 0.96, which is not 1. So it is even less of a good straight line than the other series that I looked at, and you can see like this point doesn't even hit on the line. So this trend line is doing its best to make a straight line out of these data points. And then as far as the equation goes, remember y equals mx plus b, so we've got a slope here of y equals 1.4194 times x minus the b, so the slope is 1.4 something. I'm going to edit that so that my brain can handle it, and it rounds off to 1.4. So I've got 1.4 times x, and I know that my slope now is 1.4. So in this case, we've got a slope of 1.4, which is higher than 1. And remember, our perfect thermometer, which is shown in blue, has a slope of 1, and that equation is still down here, y equals 1 times x. So we've got an mx, or slope of 1, and that is a 1-to-1. So you've got, for every run across in the actual temperature of the water, you have a corresponding rise. So rise over run is perfectly 1-to-1. In this case, you can see this slope is higher. This is steeper, so you've got a slope higher than 1. In this case, we've got a rise over run of almost 1.5 degrees for every run across on the x-axis of 1 degree of reality in the actual temperature of the water. And then in terms of the y-intercept, it's got a y-intercept of negative 6.4. So if you trace this line back to the y, or vertical axis, it hits at negative 6.4113. And the equation of a straight line, you can see that's 0.96, which makes sense because like this middle point doesn't even hit the straight line. So this trend line is a linear trend line, and Excel is trying its best to hit all the points, but you could see they're kerflooey. So this is indeed not too good of a perfect straight line. Frankly, it's still pretty good, but not for thermometers because those are really simple devices and they should be measuring right on. Thank you for watching.